as we said before, we made some assumptions about the error term, and we want to test for these assumptions, whether they are true or not. So in the first half of the lecture, we looked at the heteroscedasticity, or the variance of the error, whether it is constant or not. Okay? And we saw the tests, what tests we can use. But in general, we say if we have cross-sectional data, so then you should expect to have heteroscedasticity, but this is not, you can't just make a conclusion based on that. You say, okay, Hani said, because if you have cross-sectional data, you have heteroscedasticity, so you shouldn't test. No, do the test. Okay, so please do the formal test and also know your data. So with this one, with autocorrelation, again, it's another assumption about the error term and how it behaves. We assume that, assumption 5, that the covariance between ui and uj, so we talk about two errors, should be 0. So the correlation between the errors should be 0. And that means if we had a disruption in output because of some sort of strike in, let's say, in this week, this shouldn't affect the output for the next period if you're talking about monthly data, let's say next month. Okay? So in that sense, the disruption in output caused by a strike in time t should not cause any issue, or should not be correlated, or should not affect output in time t plus 1, so in the next period. Okay? Or if we talk about, this is time series, if we talk about cross-section data, so if the effect of an increase in one family's income, the effect on their consumption should not be correlated, or should not affect the consumption of another family. Okay? And as you can expect here, this is a problem that usually comes with time series data, not cross-sectional data. So in most cases, in most time series data, you have the errors correlated. So we want them uncorrelated, but they are in time series. Because of the nature of time series data, they are ordered in time. So it's likely the case where you have, if you have a shock, or if you have a change, or if you have something happen for you, the error term in time t, this will be carried over to t plus 1, to the next time period. So again, heteroscedasticity, when we talk about the non-constant variance, something that is likely to happen with cross-sectional data. In this case, autocorrelation is more likely to happen with time series data. Okay? We're using here data called Open, and this is again in the same package, POE data. And I know some of you had issues installing the package. I'll show you in the tutorial how to do that. So we have data about, I think, inflation or growth and unemployment. So this is growth rate, output growth rate. So if you look at this, you'll see some sort of clusters or persistent positive and negative values, which continue. So for example here, if the output growth is declining, so in one period, so it's likely to carry on to the next period. The same thing here, or if it's going up, increasing, is the same thing. Because this is the time, so with the same thing with unemployment data, so here it's declining, again next period is declining, next period is declining, and then if it's increasing, so it's likely to, so there's some sort of correlation here over time. So again, just looking at the data, well, you should look at your data, you should examine your data, but at the same time, you need to do some sort of tests. Here again, I'm just doing the same thing. I'm plotting the data for the growth rate, and its lags means in time t minus 1. So this one, time t minus 1, so we compare between growth this time, these are quarterly data, so growth in this quarter compared to growth in the previous quarter, so t minus 1. This growth in this quarter compared to, or against to growth in 2 quarters before, okay? So t minus, minus 2. So there's some sort of correlation here. So if you plot a line, kind of years to represent this data, there'll be some sort of positive correlation. What is the problem then? So we understand now that if the assumptions we made about the error term is that the errors should not be correlated. So the question now, what if they are? Okay, what if they are correlated? How this is going to affect our lovely OLS estimators? Okay, so again, OLS estimators will be unbiased, but they are not efficient. So they are not blue. We want them to be blue. They are not the best anymore. They are not efficient. So what is efficiency here? What do you mean by efficient here? So we understand unbiased estimator, do we? Okay, so what do you mean by efficiency here? Yes, the minimum variance, thank you. So it's the minimum variance, okay? So it's no longer have the minimum variance. So that means it's not blue anymore, it's not the best anymore, okay? So in this case, the standard errors are usually underestimated. They are not reliable, and that means hypothesis testing are not reliable too. So what should we do? How to detect for autocorrelation or serial correlation, the correlation between the errors? Okay. One way is to plot. You can look at the Correlogram, or you can do the formal test. The test we'll cover today: the Durbin-Watson test and Bush-Godfrey LM test. So, looking just plotting just the Correlogram for this data, for growth rate data from open data set, you will see, if you look at these two, so each bar of these correspond to one lag. This is going back, these are the number of lag, starting from 0, going back to the fourth lag or beyond that. Okay, so kind of, okay, so if you look between these two lines, so it's not above this line, so there's no correlation here. But here, it seems between the first and the second lag, there seems to be some sort of correlation, because you see it's above, it's outside these borders here, so on this one and this one. But in the rest, they are within these borders, so that means, okay, so the first or the second lag might be autocorrelated. So there might be some sort of correlation in between the time t and time t minus 1 and time t minus 2. So in Durbin-Watson, there are some assumptions. So we're talking about two tests, Durbin-Watson and LM test. So with Durbin-Watson, the assumptions were made that your regression include an intercept, and the errors are normally distributed, and there is no lagged value of y between the regressors. So there's no lagged dependent variable among the regressors. So you don't have yt minus whatever, minus I. That means could be minus 1, minus 2. So there's no lags of y on the right hand side. And your error take this form. So this is the error in time t. Depend on the error in time t minus 1. So that means if you have quarterly data, so the form of the error, that the error term in this quarter depends on the error term in the previous quarter. And this, we need to test this row here, this coefficient here. If this coefficient is 0, okay, that means it does not, there's no correlation, yeah? So if you find that this row is 0, so there's no correlation between UT and UT minus 1. But if it's not 0, that means there's correlation, or autocorrelation. Okay, so autocorrelation means the error is correlated with itself. Okay, so serially correlated. So you're testing this coefficient, and Durbin-Watson usually give you two tested statistics, D low and D upper, and then you can actually see using these, you can actually decide whether you have autocorrelation or not. But So your null hypothesis is no autocorrelation. Okay? So if the value of the tested statistic is close to 2, that means you accept that null hypothesis. What is the null hypothesis again? No autocorrelation. So there's no autocorrelation. So if you accept that, that means there's no problem. But if you're away from this 2, okay, so if it's more or less than 2, okay, that means it's there's like an indication that there's a serial correlation. In our example, I think I'm using here different data set called Phillips, and I just pulled the data, and again, this is quarterly data. I plot 2 variables. This is the inflation rate, and this is the unemployment rate. So this is the change in the unemployment rate. So this is the inflation rate, and this is the change in unemployment rate. So I estimated this model, inflation equal beta 1 plus beta 2, the change in the unemployment rate plus some error. Okay? Estimating this model, give me this estimation, and it seems that, well, the change in the unemployment rate, this one, the estimated coefficient here, and the p-value is very small, so it seems that it's statistically significant, but can we rely on that? Not yet, because we need to test for autocorrelation. So we need to look at the error from this model. So looking at the error here, again, what does this tell us? So that means it's likely we have autocorrelation here. See, it's above these lines. So and these are different lags. Remember, these bars represent different lags. So that means we kind of have some pattern with the correlation with the errors, and that means we are likely to have autocorrelation. But this is not a test. This is not a formal test. We need to do the formal test. Doing the formal test, this will show you how to do the Durbin-Watson test. So I did the estimation first, and I give it a name. And all what I did here, I call it Phil whatever from Phillips, and I call it Durbin DW test. That's the function that produces the Durbin-Watson test. So what we need to look at here is the p-value. So this is the tested statistic. Is it close to 2? It's 0.8. It's not close to 2. So that means there's serial correlation. But if you want to, you don't need to go to look at the table and then decide in which region you are, because you could just simply look at the p-value here. The p-value here is very small. Okay? So this is very, very small numbers, nearly 0. This is 0. Okay? So what does that mean? You reject the null hypothesis. Okay? Very small p-value means you reject the null hypothesis. What was the null hypothesis? Yes, no autocorrelation. So if you reject the null hypothesis that says no autocorrelation, that means autocorrelation is present, it exists, and it's a problem. Okay? So this is the first test, Durbin-Watson test. We said there are 2 tests, the LM test and the Durbin-Watson test. Moving to the next test, which is the LM test, actually you're more likely to be relying on this more, because all these assumptions here about the Durbin-Watson test. Remember, to apply Durbin-Watson test, you need to satisfy these assumptions, and also your error. The assumption here that your error is first order thing. So the error depends on the error in t-1 only. So there's no more lags than this. But with LM test, you can actually go beyond that. So that's why I'm saying you're more likely to be relying this. You're likely to be relying this more often. This test, the LM test. So what does the LM test? The Bush-Goodfried LM test. So as I said, it allows to have YT minus I among your regressors. So it's fine. So this was one of the conditions in Durbin-Watson test. So you can't have this. But now with Bush-Goodfried LM test, it allows for it. And actually, it also allows for higher AR scheme or autoregressive scheme. So that means you can have more than one. So in this case, if this is the error or the the error. So that means the error depends on the error in time t. The error in time t depends on the error in time t minus 1, time t minus 2, and then you can go back as far as you think is important. So if you think you're serious, let's say, correlated with what happened in the past, in the t minus 1, t minus 2, whatever, how many lags, 5 lags, you can go back 5 lags. So in this case. So in that sense, okay, so you get this estimation, you estimate this model, okay, and your null hypothesis is still the same, no serial correlation, no autocorrelation. That's the null hypothesis, the same like Durbin-Watson test. And then from this regression, you could have t, which is the number of observation, time multiplied by r squared from this regression, and that would be your test statistics, LM. In that case, if you have, again, if we look at the p-value, because again we use the p-value to decide in this case. If you look at the p-value and your p-value is very small, then you reject the null hypothesis that no serial correlation. That means there is serial correlation. So this is an test, I think, yeah. I tried different options, so I'll explain this in the tutorial, different methods of applying LM test, but these all are LM tests anyway. So when you look at the p-values, this is a very small number, but just so you can't see it because of the, I should have corrected that table, but it's very small, so it does confirm what we concluded from Durbin-Watson test anyway. So just to summarize this, so what is autocorrelation? What do you mean by autocorrelation or serial correlation? The same? Yes, so the error terms correlated. And is this problem likely to be in cross-section or time series data? Time series data. Okay? So how to detect? We talked about formally testing for that, two methods or two tests. Durbin-Watson, it's a bit restrictive because it has some sort of many assumptions that you need to make sure that they apply to your regression, and the LM test, okay? But the null hypothesis is the same in both tests. So what's the null hypothesis? No serial correlation or no autocorrelation. So if you have a small p-value, what does that mean? You reject the null hypothesis. That means there is autocorrelation. So if there is autocorrelation, there are different ways to deal with autocorrelation. You could add lags. You could include lags, and this is something we will talk about next lecture when we talk about dynamic models. When we have the dependent variable in time t, and then among the regressors you have yt minus 1, yt minus 2, and we have more like dynamic model. So we'll talk about this next lecture. So you could include more lags, and that way you actually explicitly accounting for these effects rather than leaving this to go into the error term. So you're actually including it in the model. Or there's another way to do this. We could actually use what we call HAC. So it's heteroscedasticity, autocorrelation, consistent standard error. So HAC here stands for these three words: heteroscedasticity and autocorrelation, consistent standard errors, and that will correct the standard error. So these are the same estimation, but these are different ways for these hacks. So then that will produce different standard errors. So that means this will mainly correct for the standard errors. So again, because the problem with the presence of autocorrelation, the problem is your OLS estimator is still unbiased, but it is not efficient. Okay, so it's not the one with the minimum variance. So that means your estimator are not blue. So you drop the B from here, so it's not best anymore. Okay, remember the best means blue means the best means the efficient or the one with minimum variance. So if it's not the one with minimum variance, so it's not blue anymore. Okay,